Hey guys, I'm back with a new video. In the previous video, we learned about the splitting of our dataset and how we can collect the data for a machine learning analysis. So in this video, let us learn how we can classify or basically distinguish our machine learning model based on three categories. So let me clear the screen first. Okay, so clear canvas, and the topic is different types of machine learning methods. Now we can distinguish our machine learning model based on three categories. So number one, based on the type of model. Based on type of model. Number two, based on the presence of output variable. Output variable. Then number three, based on the type of output variable. Okay, so let us first understand the very first type, which is based on type of model. Now you want to differentiate the machine learning model based on the type of machine learning model. In the previous video, we understood the pipeline of machine learning model. We learned that we work on with some data and we have a machine learning method or technique. We also learned about the collection and splitting of our dataset in the previous video. Now we have two types of methods that come under this. So under the number one point comes two methods. One is parametric method. And the second one is non-parametric method. Non-parametric method. And this is also known as instance-based method. So instance or observation-based method. Now to understand the parametric method, let us take an example where we have two input variables, say x1 and x2, and let x1 represent the temperature, and I will plot that along the x-axis, and x2 represent the humidity. So let this be humidity, which I'm denoting using H, and x1 denote the temperature, which I'm denoting using T. Okay. Now what I want to do is, in our data, the x1 represents the temperature and x2 represent humidity, and we want to make a machine learning model around the data. So let us assume that the relation between x and y is a linear relationship. Okay, so we are doing some assumption first. From knowledge of mathematics, you must be knowing that a linear function is of the form y is equals to m0 plus m1 x1 plus m2 x2 plus m3 x3 and so on. Now this is how we represent a linear function. Now our problem is reduced from finding the function to finding these parameters, which are m0, m1, m3 and so on till say mn. Now this means that in order to find the function, which is y, in order to find this, that is the estimation value, which is say y cap, I want to find the estimate value. Now the problem is now reduced to find a set of parameters that are denoted using mi. So I want to find the set of parameters that are denoted using mi, where I will vary from 1 to n such parameters. Okay, not 1, 0, because we are starting with 0 to n such parameters, or to be precise, 0 to n minus 1 such parameters. Now once we get the set of parameters, you can easily predict the output variable, which is y, using these parameters by substituting the values of these parameters into the function once you get them, and getting a function which is also known as the parametric function. Now, so these parametric methods finally can be described using some mathematical function which has a certain well-defined trajectory that you can trace a graph and analyze it. Okay. Now some key points that you need to understand is like this. Like if the graph for temperature and humidity is linear, it varies in a linear proportion. Okay. So in direct proportion you can say, then this line must have an equation. Okay. And that is why the shape of the function is assumed beforehand. So we can say that's a parametric method because we can represent such models using some equation, using some functional form that has an equation. Okay. Now some key points that you need to understand is for a parametric method is that the shape of function is always assumed when you start with the parametric method. So I will say shape assumption. Okay, this is one of the key points. So let me enclose this in a box. Now after you make this assumption, what remains is to determine the parameters of the function. So we have to determine these parameters, which are m0, m1, m2, and any number of such parameters. You have to determine the parameters of this function. At the end of your machine learning process, which you are continuing, you can predict the value of the output variable y, or you can say an estimate of y, by plugging the values for input variable in the equation, okay, that we get. So this is how the parametric method actually works. So example for parametric methods are linear regression. So linear regression, which we will see in later videos. Okay, so this is the example for parametric methods. Now let us move forward to non-parametric method. So what I will do is I will clear up the screen. So make a note of this and I will clear the canvas here. Okay, now let us move forward to non-parametric methods. Non-parametric methods, and this of course comes in the category of based on the type of model. So we have distinguished the machine learning models based on the type of model. So we have the second method under this category, which is the non-parametric method, and also known as the instance-based methods. Instance-based. Okay, now here the above assumption is not taken into account. Here we are not going to assume the functional form for the model. Okay, so an example for this can be prediction of whether a particular day is sunny or rainy. So predicting whether a particular day is sunny or rainy. So let me enclose this in single quotes. Okay, so as an example, let us see how we can represent this using a graph. Now what I will do is I will use two notations here. Using star, I will represent that on a particular day, that particular day was rainy. Okay, and dollar will represent that a particular day was sunny. And let us use the same graph that we had. So the temperature is plotted along the x-axis, the humidity is plotted along the y-axis, and let us represent the stars here, which represents a particular day was rainy. Okay, so some stars, and let us trace some dollars as well. Okay, So some dollars. Okay, so what we want to achieve here is that given a value of temperature and humidity on a certain day, can we predict whether a particular day will be sunny or rainy? So we will see later when we cover about some non-parametric methods that if a certain point, like say if we have a point represented using dot, is close to the density region of some category, say it is close to the density region representing that a particular day is sunny, then what will happen is it is more likely to go into that category. Okay, so it will become a part of this category and will get converted to a dollar. Okay, so now this all depends on the algorithm that you're using. We can also draw a boundary that can separate these two categories. So this is a demarcation boundary that is separating these two categories using some line, but this line will not have an equation. Okay, and that is why it is called as a non-parametric method. You can understand it this way, that it is some form that you cannot comprehend mathematically. That is why it is called non-parametric and instance space, because you will be consuming or you will be using all the instances that you have in your training data. So in the end, we are not going to get some functional form. What we are going to get is that we are iteratively using all the instances that we are having in the training data again and again, iteratively, to predict for new values. And that is why this is known as instance-based method. So let us learn now how we can differentiate machine learning models based on the presence of output variable. So what I will do is I will clear up my screen. Based on presence of output variable. Now this is the second category based on which we will distinguish our machine learning models. So based on the presence of output variable. Now let us again use the same prediction problem of predicting whether a particular day will be sunny or rainy based on the temperature and humidity as the input variables. So now suppose we have a big data set where we have, so let me make a dummy data set. So suppose we have this data set and here we have many columns and so on. Okay, now we have a big data set where we have more than these two input variables. So we have temperature, we have humidity, let us say we have wind speed, then we have atmospheric pressure and some other weather patterns, and we want to predict, so some other weather patterns are also there. Okay, so I'm denoting that using dots, and we want to predict whether a particular day is sunny or rainy. So let this be y, so output variable, and these are your records of dataset. So each such row is representing a record. Okay, now you want to predict whether a particular day is sunny or rainy based on these input variables. And let us say we also have whether a day was rainy or sunny. So let us record that into our data set. Okay, so we are given this, that this particular day we had rain, this particular day was sunny, rain, sunny, and if we have more such columns, we can keep on extending this: rainy, sunny, and so on. Okay, so continuing further, now suppose we have this column as I showed you. Now what I want to do is, we are given these output variables. Okay, now if you have all this data, you can build a model so that you can predict for unforeseen input variables whether a particular day of the future will be rainy or sunny. But one thing you must be wondering about is that what is the role of output variable? This output variable y for building your model. Okay, we are having this output variable for entire data set that we are using for building our model. So this y is called as label or target variable, or you can say output variable, and we will discuss, and we have discussed this in one of the previous videos, and you can easily judge that this is a supervised learning problem because these labels are supervising our machine learning training process. Okay, we are given these output variables as labels based on which we'll predict for unforeseen values. Now where you are given the output variable or label as well for your past training data. Now using all the observations that you have in the dataset that has the past data recorded inside it, and give it to your machine learning model, and you're supervising the learning process of the model based on these labels. So the model can build a statistical power of prediction for the new coming future data based on the old observations that you're having. The old data is the guiding force that makes it more performant when the model encounters new unforeseen data, and then it is able to perform better as well. And if you don't have the labels for your past data with you to predict for new unforeseen data, then that is called as unsupervised learning. So to conclude, if the label or the output variable is present to guide the model in its learning process, then that is called as supervised learning. Otherwise, it is called as unsupervised learning. Now we'll learn about supervised and unsupervised learning in great depth in coming videos. Now let us discuss about different types of supervised learning in a bit detail. So what I will do is I will clear up my screen and different types of supervised learning. So I'm saying SL, okay, for supervised learning. Now let us discuss some key points about regression, which comes under supervised learning, and classification, which also comes under supervised learning. Now let us understand a simple use case of house price prediction. So I will say house price prediction under the head regression. So house price prediction. So let us assume some input variables. So I will define some input variables. So just I'm enclosing them in a square box. So let us say we have per square feet rate of your property. So this is one input variable. Then say we have locality, where your property or where your house is located that you want to sell. Then say we have rooms count. So this is your third input variable. So the locality of the city in which it is located, and rooms count is the average number of rooms per house. And we have an output variable. Okay, I'm denoting that using OE. So it is the house price. So you want to predict the house price based on these input variables. Okay. Now since we know that house price is some numerical value, so it can be say these many dollars, or say these many dollars. So this is something that you can compute that has a magnitude, some numerical form. It is a continuous variable and it is quantitative in nature. Okay, so it is continuous in nature, and it is also something that you can compute or you can measure. So it's quantitative in nature. So continuous and quantitative in nature. That means it can take infinite number of values for different set of input variables. Now since house price is a continuous variable, this comes under the category of regression. So to sum it up, any supervised learning problem which has an output variable of continuous nature. Okay, so our house price is something that is continuous in nature, and that is why it's a regression based problem. Now let us move forward with classification. Let us consider an example for this also to understand. My main motive is to make you understand everything from practical standpoint rather than from the book written definitions of these concepts. So for classification, we already discussed about the prediction problem. So whether a particular day is sunny or rainy based on the dataset. So for that problem, we took various input variables like temperature, then we took humidity, then we took atmospheric pressure, then we also took wind speed. So these were our input variables in that case to predict for a particular day whether it would be sunny or rainy. Okay, so these were our output variables that we were predicting for. So that was a classification problem. Now here your output variable is discrete in nature. Okay, so output variable, which I'm denoting using OPV. Let us be a sum consistent. So I will say OV. Okay, so it is discrete in nature and not continuous. So output variable is discrete in nature. Either it is inclined towards sunny or it is inclined towards rainy. Okay, but not anything mid between, and hence not continuous for that matter. So discrete variables are basically those variables that can take a finite value from a range of values. So we'll discuss about different types of unsupervised learning in the next video. But first, we'll focus we'll start from supervised learning in the next video. So this was all about the video on how we can distinguish our machine learning models based on different criteria. Okay, so these are the different types of supervised learning that we discussed, and in the next video we'll start with regression and supervised learning. So I'll see you guys in the very next video.